what I could show next is the backbone curve. So this is another application now, and this is purely mechanical. So what do we have here? We have a clamped beam. And if you check the usual resonance peak of a clamped beam, then you have a resonance frequency, the first mode vibration, here around 162 hertz. And well, here there's some damping. So you can see, obviously, this is very usual. At the resonance frequency, you have the highest oscillation, and that's it. This is a linear regime problem. Now, if you check the same problem, but you include geometric nonlinearity, then you have something actually very different. You have a backbone curve. And this center of the peak is still at the same frequency. But the thing is that because of the geometric nonlinearity, there are two possible solutions for some frequency. There's the solution where the vibration is really tiny, and this is just the same as in the previous graph. But there's also the solution where the vibration is really bigger. And so due to the geometric nonlinearity stiffening, it can still vibrate and resonate at that frequency because of the nonlinear behavior. Now we will explore this and we will see how that works in quantized also. Now it is worth mentioning here that doing a transient analysis to get these curves is really tricky. And these curves actually occur in pretty much anything that vibrates. This applies to ultrasound transducers, but also to like turbo machines for aircraft engines. And I'm really sorry, we don't cover this part. I know there are people in the audience who do just that. And we'd love to have a talk about this with you, but this part covers really more the MEMS part of the applications. But nevertheless, let me show you this backbone curve. So very simple case. This is inspired from a paper, nice paper written by someone in the audience. And what we have is simply solid mechanics. We have a beam, it's clamped. So you set up the clamp on the left and on the right. You set up a center point load, like at the center point that is visible here. And this load basically is just a sine wave with a given amplitude. You could also set here the large displacement. This would include immediately the geometric nonlinearity in the model without doing any scripting. But since we're going to do some scripting anyways, because we have to use continuation methods, I added it immediately in the script. So we can first run the linear regime. So what do you get in the linear regime? Well, let's run it again, just again to exemplify that you can run several things at the same time because it's running not on your desktop computer, but on the cloud. So you have pretty much unlimited amount of hardware and resources available. So in one go, you can see all the jobs are starting and finishing pretty much at the same time. But this is a very simple linear resonance frequency simulation. But again, it highlights a bit the ability to run several frequencies at the same time. But now let's jump in actually the nonlinear behavior. So this is what you're going to get with if you take geometric nonlinearity into account. So you will have to run several simulations, or you will have to use continuation methods like it's used here to obtain the full curve, because obviously there are several solutions possible and you have to kind of get on the track to get on the right part of this curve. Now, the way this is done is actually very easy. This is the entire script for it. It's really as short as this. You pick your harmonics that you want to use. So here, the DC part, which is not active actually. The first fundamental frequency, double the fundamental frequency, and 3 times the fundamental frequency. And then what you do is, I edited a bit the script because we don't support for now continuation in the script just like that. So what I did was adding a while loop. So we defined the field, mechanical displacement field. You put a while loop. This was generated automatically by the script. And then I do some smart or not so smart continuation methods. Again, I don't want to compete with anyone in the audience. They are experts on this topic. but nevertheless, some kind of naive continuation methods. And the only thing that really is done here is that you have a field that is defined, you solve for your equations here, and then you go to the next iteration, and the field state is used as it is. Just, you don't have to do anything. It just happens naturally. And basically this provides already some sort of continuation method. But yes, quite easy to set up. The first example that I covered was really easy, fully graphical, very convenient. This one is more advanced, mostly graphical, have the flexibility to do exactly what you want in the scripting interface. And now let's move on to the next level of difficulty. And for that, I will give the room to Abhishek.